In this section, we'll try to detect if the player is in the field of view of the NPC. So, what we'll try to achieve is to understand why and how to use vectors in Unity, understand dot products and their application. We'll also try to know how to calculate the cosine of an angle, understand why and how to normalize vectors, know why and how to add vectors, and finally, know why and how to convert angles to radians. So, what is the scenario? Well, the scenario is as follows. We have an NPC, as you can see symbolized by a red dot on this picture, and a player entering the field of view of the NPC, symbolized in blue, and as you can see the field of view is symbolized by a green area. And the idea is to detect whenever this player will be visible by the NPC. So as you can see in this demo, we see that the NPC can detect the player when the player enters the field of view. We can see this even more clearly using the scene view, and as you can see, the field of view is symbolized by green lines pointing at 45 and minus 45 degrees. And you can see that whenever the dot, which is blue, enters this field, the red dot, which is the NPC, starts to follow the player. So what we need to know really is when does the player enter the field of view, or FOV. If we call the field of view alpha, knowing whether NPC is in the field of view is equivalent to know whether the angle determined by the direction of the NPC and the vector that points at the player from the NPC is comprised between alpha divided by 2 and minus alpha divided by 2. So far, a field of view of 90 degrees, the angle defined by V1 and V2, should be comprised between minus 45 degrees and plus 45 degrees. This is explained on the next diagram, and if we imagine the vector V1 counterclockwise, if the player enters the green zone, we know that the NPC is in the field of view. So, as described on the previous diagram, and knowing that the cosine of 45 degrees is approximately 0.7, and that the cosine of minus 45 degrees is approximately also 0.7, we know that the player is in the field of view if there is an angle between V1 and V2 that is between minus 45 degrees and plus 45 degrees. Or, in a similar way, if the cosine of the angle between the vectors V1 and V2 is comprised between 0.7 and 1. This is because when the player is on the right border of the field of view, the angle between V1 and V2 is minus 45 degrees, so the cosine is 0.7. When the player is in front of the NPC, the angle between V1 and V2 is 0, so the cosine is 1. And when the player is on the left border of the field of view, the angle between V1 and V2 is 45 degrees. The cosine is 0.7. So effectively, when the NPC is in the field of view, the cosine of the angle will vary from 0.7 to 1 and then back to 0.7 again, if we consider the player going from right to left. The field of view, of course, could be any number that you decide. In this example, we have arbitrarily chosen 90 degrees to simulate the horizontal field of view for some humans. But you could, if you wished, increase it to 100. Now that we have clarified the calculations of the cosine, let's explain how we can find the vectors v1 and v2. v1, as you can see, is in the direction of the NPC. This vector originates on the diagram from the NPC and is going in the direction of the positive z-axis. v2 is determined by the position of both the NPC and the player. Let's see how. As you can see on the next diagram, v2, vNPC, and vPlayer form a triangle. vNPC is the vector for the position of the NPC. It starts at the origin of the coordinate system. vPlayer is the vector for the position of the NPC, and, as for the previous vector, it starts at the origin of the coordinate system. If we operate a loop from the origin of the coordinate system, we can go from the origin of the coordinate system to the NPC by following the vector vNPC, then follow the vector v2 in reverse, which means that we go from the head of the vector to the tail, and then following the vector vPlayer in reverse again, which means that we follow it from the head to the tail. So we could say that vNPC plus v2 minus vPlayer equals 0. In other words, by following vNPC, then v2 and vPlayer in reverse, we end up at the same point. Following this, we can then say that v2 equals minus vNPC plus vPlayer. This is how we can calculate v2. Normalizing the vectors. So at this stage, we know v1 and v2, and we just need to calculate the dot product between these two to have an idea of the cosine of the angle. However, if you remember the definition of a dot product, the cosine of the angle between v1 and v2 equals the dot product only if the magnitude of the vectors is 1. Or, in other words, if these vectors have been normalized. Normalizing can be done easily in Unity, as each vector can access the function or method called normalized, which returns a normalized version accordingly. So at this stage, we have two normalized vectors. Their magnitude equals 1. And we need to calculate the cosine of the angle defined by them. You will notice that so far, we have been using degrees for angles. Notice that the field of view, FOV, equals 90 degrees. However, the function that calculates the cosine in Unity only takes radians and not degrees for parameters. So we will need to convert our angle in radians first before the cosine can be calculated. This can be done using the function called mat_deg_to_rad in Unity. So now we have an angle expressed in radians thanks to the previous function, and we can calculate the dot product of the normalized versions of v1 and v2. So that's great. And bearing in mind that then when the player is on the right border of the field of view, the angle between v1 and v2 is minus 45 degrees, so cosine is 0.7. When the player is in front of the NPC, the angle between V1 and V2 is 0, and when the player is on the left border of the field of view, the angle between V1 and V2 is 45 degrees, with a cosine of 0.7. So we effectively know that for the NPC to detect the player, or the player to enter the field of view of the NPC, the cosine of the angle between V1 and V2 should be comprised between 0.7 and 1.